Hey everybody, welcome back to Young Engineers of Today. I hope you had a good weekend and hope you had a good holiday. It was nice and relaxing, and maybe there was a snow day or two in there, although I think uh, I think that was highly inconsistent across the state, so I don't know. Anyway, um, welcome back, and we are going to take a different track for today, just for today. We will resume with our regularly scheduled Fusion 360 and CAD and CAM and all that kind of stuff next week. However, there was a very important discovery earlier in the week. In fact, I believe it was over the weekend. At any rate, it's a very important discovery. Actually, um, we said that it was the most important one so far this century, and has some pretty big implications as far as physics are concerned. That discovery, in case you aren't aware, was gravitational waves. So we're going to devote today's lesson to basically learning what happened, uh, why it's important, and what it might mean for the future of physics. So what exactly happened? Well, scientists detected gravitational waves for the first time ever. Sorry about that. My computer is flipping out. Hopefully you guys didn't hear, hopefully the audio didn't cut out for you guys or anything like that. Detected gravitational waves for the first time ever. It was predicted by Einstein in his theory of relativity in 1915, but it was never really truly observed due to a lack of technology, of course, until now, 100 years later, 101. It's the first observation of the universe outside of the electromagnetic spectrum, which is kind of interesting when you think about it. Every time we have looked at anything or heard about any discovery or anything like that, it's always been an observation in the electromagnetic spectrum. Uh, we look around at everything in visible light. You think of night vision cameras. Well, those are infrared. Uh, they take pictures of the inside of your body at the hospital with X-rays. Um, you eat your food with microwaves. You get new music over the air with radio waves. Everything, pretty much everything that we interact with that involves our own technology um, on a daily basis is all electromagnetic based, because that's how our observations have always been. Um, we can observe how quickly something falls, but we can't actually observe gravity, you know, doing its thing, affecting the flight path of it. We just see the result, which is something falling. We can model it with mathematics, but we've never actually seen it before. So that's actually kind of cool. The fact that we, for the first time ever, have observed something that is not a part of the electromagnetic spectrum. So where do they come from? Well, these waves occurred due to the black holes, in a binary black hole system. Not just that, it was from those black holes smashing into each other over 1 billion years ago. What are binary black holes? Well, raise your hand if you're familiar with binary star systems. All right, one hand. Okay, so for those of you who aren't familiar, here it comes. A binary star system, what we have right now in our solar system, is just a regular star system. You get the sun, and then you got all the things orbiting around it. Whoop-de-doo. Well, in a binary star system, you'll have two stars. In most binary star systems, one of those stars is actually orbiting around the other star. In some binary star systems, those two stars are kind of like locked in the stance where they're sort of orbiting around each other, or they're spinning because of, the gravitational pull of the other star. And so they start spinning around and around, and, obviously their star system, because the entire galaxy is spinning, they're also moving. It's actually a pretty elegant little dance, if you'd like to think of it that way. At any rate, there are star systems that exist out there where there are, two stars. Either one's in orbit around the other, or they're both spinning around maybe like a central point. You might imagine a point right here where they're both spinning around that point. It doesn't actually exist, but it kind of does mathematically speaking, because that's the point where their center of gravity is no. Oh Lord. Okay. Apparently there's something going on with my microphone right now. It's freaking out a little bit. Anyway, the center of gravity that these two stars have, and they orbit around it, which is kind of strange to think about, considering there's nothing actually there in the center of gravity, and the center of gravity is created by the two masses, except they're orbiting around it. You can think of it like a you ever know those balancing birds? They're like the little plastic birds, and you can stick one on your finger, and it will always like stay balanced on your finger. And then you can spin the bird around, and even though you spin the bird around, it stays balanced on your finger. It's because even though most of the mass is on like not where the beak is, the center of gravity is where the beak is, so it stays balanced there. They're actually kind of things. Anyway, I'm getting wildly sidetracked. Binary black hole system, it's the same idea, except these are instead black holes. Notice how I colored them black, because visual aids are helpful. So same basic idea. Now you've got two black holes which are in relatively close proximity to each other. In this case, they're not actually that close, because then they sort of get smashed into one another, and then they would turn into a larger black hole. But in this particular situation, these black holes were actually that close to one another. They were close enough that they were able to, eventually, the gravity was strong enough that they were able to slowly get closer and closer to each other, until eventually they just collided into one another. They just mashed together, and then they made a larger black hole. The offshoot of that is that they made gravity waves. So not only was this the first time I've ever observed gravity waves, this was the first time that binary black holes have ever been confirmed to exist. This is the first time, these were the largest black holes that we've ever discovered. And it released an immense amount of energy. In order to get sort of an idea of that right now. Oh boy. Excuse me for a moment. My microphone is not having a good day right now. I'm waiting for it to figure its life out. I don't know what's happening here. I know at least that you guys can hear me, because it's still picking up information from the microphone and showing it my little audio equalizer thing. But that's not okay. Right. I think the storm has passed. Let's continue. It released an enormous amount of energy. Imagine the entire Milky Way galaxy blowing up all at once. That's how much energy was released. Now, it was in a very, 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 very short period of time. So all in all, there wasn't that much power expended. You can think of energy like how fast a car goes, and power being how far that car goes. So the car can release a lot of energy. It can go very fast, but it can be for a very short period of time, so it doesn't go very far. So there's not a lot of power. But regardless, that is an immense amount of energy. 66 billion suns. To channel Carl Sagan for a moment, billions and billions of stars, all exploding at once. Like, that's crazy. That's a lot of stars. I mean, I don't need to tell you that a billion is a lot. I'm sure you guys can understand how much that is on some sort of level. It's like it's even hard for the human brain to comprehend a number like a billion, 1,000 million, a thousand, thousand, a thousand thousands. It's and then another 66 on top of that. But anyway, these black holes were far bigger than any other we found so far. So each object was 29 to 36 times the mass of the sun. You take the amount of stuff that makes up the sun, not necessarily the size or anything like that, but the number of atoms that make up the sun. And you multiply that by anywhere from 29 to 36 times the number of atoms. It's a lot of atoms. On the other hand, though, the sun is what? It's like 100 times the diameter of the Earth, more than that. Like it's massive. Well, it's voluminous, I should say. It has a large volume. It's also massive, but it's voluminous. Anyway, you take that increased amount of mass and you squeeze it into a 150 kilometer diameter. So the distance from Greensboro to Charlotte. You take something that is that big and has that much stuff in it, and you slam it into a space smaller than the state of North Carolina. This, in essence, is a black hole. Now, not only that, they're spinning around each other at half the speed of light, which is crazy. I mean, everything about astronomy is mind-boggling. You have this insane amount of mass that was slammed into such a tiny area, and then they were going half the speed of light, spinning around each other. Like, astronomy really doesn't deal in half measures. Everything's crazy. Anyway, they fully merged after their orbits reached about the distance from Asheville to Charlotte, so about 210 kilometers between one another. So they eventually got close enough that they turned into one black hole. And that merger released 3 solar masses of energy in the form of gravitational waves. Whew. So, what is gravity? We'll take a look at the different sort of ideas of gravity as they've gone throughout the ages. Or the centuries, rather. So Newton's idea of gravity was really the first thought of gravity as a force or anything like that in and of itself. I mean, obviously, gravity existed before Newton. People were aware of the fact that things fell down before Newton. But Newton was the first guy to really go, there's probably something out there in the universe that's causing stuff to fall on other stuff. And that's where he came up with the idea of gravity. So gravity is a force that is felt between any two objects regardless of size. Now, this is Newton's idea. Gravity is a force felt between any two objects regardless of size. For example, you and your best friend have always had a gravitational attraction that gets stronger the closer you are and the more both of you weigh. So, it's sort of a strange example, but yeah, it's true. Everything exerts some sort of weak amount of gravity on everything else. It's really only felt on a larger scale, though. It's also felt the closer you are to something. So, if you really, if you want to increase your gravitational pull on something, you get closer to it. Conversely, it will exert more of its gravitational pull on you. So, Newton's idea of gravity accounts for the movements of celestial bodies, and it is still used for gravitational approximations in physics classes today when extreme precision isn't required. Because again, it's close enough. That's actually the case with a lot of physics in you know, like high school and college and stuff like that, you'll use Newtonian mechanics because it's on many scales close enough. Like it doesn't really matter. You know, when you're trying to calculate a ball, it's the trajectory of a ball as it's thrown through the air. You can use Newtonian mechanics because, but Newton couldn't really describe why these ideas worked. So to quote, gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial, I have left to consideration of my readers. Basically, um, was it a physical force? Was it gremlins? Was it God? He didn't really know. So he kind of left that up for other people to figure out. He just made the numbers work. He also made calculus, so, you know, I can't really blame him for not figuring out the idea of physical forces when no such idea existed before then. Anyway, there wasn't a whole lot of development in the field of gravitational forces and calculation, and then the theoretical side of gravity until Newton came along. There were other ideas, but none were really as earth-shattering and changing as Newton's were. And the thing is, it became his ideas about gravity were packaged with a larger set of theories. Well, a larger theory, the theory of general relativity. He had actually two theories about relativity. He had the special theory of relativity and the general theory of relativity, or the theory of special relativity and the theory of general relativity. You know, it depends. Special relativity. The laws of physics do not change depending upon the observer's frame of reference, which this is, you know, relativity in the, you think of like the relative speed or something, or somebody's perspective, like maybe, you know, the fact that you're $20 short can really suck for you, but it doesn't necessarily suck for somebody else. It's all relative. At this point I'm rambling a little bit. Anyway, that's where the idea of relativity comes in. It's all about relative speeds and, you know, the relative passage of time and everything like that. The name relativity isn't just a fancy word. It's all about how everything is relative to everything else. So special relativity is the laws of physics do not change depending upon an observer's frame of reference. What does that mean? Well, okay. First of all, interestingly, whether you're on Earth or you're flying in a spaceship at like 99% of the speed of light, certain things will stay the same, like the speed of light. In fact, it comes in through, I believe, general relativity. It doesn't actually talk about it in general relativity. Yeah. In fact, your observation of how fast light is going stays the same, which is weird. So, like, you know, if you're on that spaceship and you're flicking a flashlight on and off the wall, even though the speed of light is really the speed limit of the universe, nothing can actually go faster than the speed of light, with like one or two exceptions that we think are exceptions. Physical objects like you or I or the Earth or you know, cats or whatever cannot go faster than the speed of light. Light cannot go faster than the speed of light. However, if you're traveling at 99% of the speed of light and you flick on a flashlight, that light, relative to your position, looks like it's going the speed of light. Meaning, you know, you don't see like the light beams come out of the flashlight before they hit the wall and everything seems slowed down and all that kind of stuff. Like that doesn't actually happen. By the same token, somebody standing on the side will also see that flashlight shining light out, and the light will move at the speed of light. It will look exactly the same to them as it does to you. Things may look a little different depending on your reference frame. But in essence, one of the things about relativity is the fact that the laws of physics, in general, stay more or less the same, with some caveats. Relativity is a very strange theorem anyway. I mean, this is one of those things you spend time learning about in physics class and physics classes in high school and college, and it's still kind of like, well, okay, that's weird. But one of those things is that the speed of light stays constant, and the observation of light stays constant as well. So let's say you throw a baseball while you're moving at 99% of the speed of light. It'll look like it's moving normally to you. Somebody else who's standing perfectly still, it'll look like that baseball's moving 99% of the speed of light. But plus, you're throwing our speed like 95 miles an hour or whatever. But that light beam will always look the same. In essence, this is also a part of the special theory of relativity. There's more to it than this, but this gives you sort of a very vague idea of what exactly is going on. Did you have a question, Isaac? I saw that you raised your hand. All right, well, if you do, just go ahead and throw it into that question box and we'll get to it. So the theory of general relativity, Einstein developed after the theory of special relativity. Gravity is a result of a mass's influence on space around it, which is different from Newton's idea. Newton's idea is that, well, he didn't really know for certain, but the objects, in essence, would exert this force upon one another. Now, what Einstein is saying is that gravity is actually a side effect of things having mass. Nothing exerts gravity. Rather, there is this sort of thing that exists and permeates throughout the universe called space-time. And it can have a curvature to it, which is weird, but, hold up for a second. But basically, it can have a curvature to it, and that curvature is gravity. Things having mass cause a curvature in space-time. So it's more like, according to Einstein, objects having mass mess with space-time, which is responsible for gravity. It's weird. It's weird, to be sure. But there's always these thought experiments that you can use to help visualize it, and that's what we're about to go over in a second. So, but anyway, because of this, Einstein predicted, because of his model of the universe, he goes, there must be gravity waves. Like, that has to occur. If for some reason, yeah, exactly, wibbly wobbly, timey-wimey stuff. We have a detector that goes ding for it now, so we were able to see it. It goes ding when there's stuff. Sorry. So he predicted that, like, okay, so let's say that somewhere out there in space, something just suddenly, like, popped into appearance. I couldn't really do a good pop noise with my mouth because my lips are dry right now, but I tried. It just popped into appearance. Well, that sudden, like, huge change in mass should create gravity waves. Just like how, when you drop something like a stone in a pond, it creates ripples outwards. There should be gravity waves created. And these waves would move at the speed of light, because again, I don't think you're going to really move faster than the speed of light. So these waves should move at the speed of light, which is why we're able to see the result of a 1.3 billion year old collision between two black holes now, is because those waves moved at the speed of light. It happened 1.3 billion years ago. It is 1.3 billion light years away from us, and it took 1.3 billion years for us to be able to see it with our little time detector. Not really, gravity wave detector. I was trying to go with the Doctor Who thing. I couldn't remember what his device was. I just remember he says it goes ding when there's stuff. Anyway, So in order to help imagine this, what's going on here, you imagine, is this, let's see here. Yeah, okay, this works. So imagine there's this trampoline, and the trampoline is space-time. I've never started a sentence like that before, but you know, it's the first time for everything. So imagine there's a trampoline, and this trampoline is space-time. Now, you can stand on it, you can place a bowling ball on it, you can put a fridge on it, you can, you know, place a chicken on it, I don't know. The heavier an object weighs, the more it's going to bend the fabric of that trampoline. Good Lord. The more it's going to bend the fabric of that trampoline. So, in essence, that's like a large planetary or stellar body. So the sun weighs a lot. The Earth weighs a lot. The moon weighs less than the Earth, but still weighs a decent amount. All of these things, if you were to place them on a giant cosmic trampoline, would bend the trampoline in different amounts. Now, the further you get away from where you place that thing, the fabric isn't going to be as stretched and warped because, you know, it sort of accommodates for it further and further out. Everything gets kind of stretched. But like where you're standing or where that fridge is, you know, like the trampoline's all, like imagine that these are the sides of our trampoline. And this is our fridge. Whoa, what happened there? There we go. Good enough. So over here, like everything's pretty okay. And then things sort of start to curve downwards as they get closer and closer to the fridge. Until, you know, maybe you have like this like extreme sort of stretching of the trampoline right exactly where the fridge is as it's trying to accommodate it. But everywhere else, you know, it's either sort of curved or it's perfectly okay. Now imagine you dropped like a marble right here. The marble is going to go towards the fridge, right? It's just going to roll down a slope. Now, imagine that situation, but the trampoline was invisible. You drop a marble right here, and the marble starts heading towards the fridge. What does that look like? Kind of looks like gravity to me. You know, if we were to look at this from like a 3/4 view, here's our fridge sitting blissfully on our trampoline. And then we've got the trampoline around it. Scroll down a little bit. And then there's sort of like this stretching of the trampoline down into the fridge. Now, if you dropped a marble, it would head in. But if you kind of threw a marble at the edge of it, the marble might spin around on the slope. Once again, let's take away the trampoline. The marble might spin around on a slope. What does that look like? So that's why we use, that's where Einstein came from with the whole thought experiment about it being a sort of a, well, it's called the fabric of space-time, which you've heard used dramatically in movies. The very fabric of space-time will be destroyed. But I mean, it's a metaphor that really best approximates this concept that Einstein came up with. The fact that it curves in the presence of mass and it reacts presumably with gravity waves, when mass changes in a large amount, and there's all sorts of strange effects that can happen around the curvature of it and everything. That is the idea that Newton was going for. Now, again, let's say somebody's jumping on the trampoline. Let's draw a stick figure because, I'm not trying to impress anybody with my art skills. Somebody's jumping up and down on the trampoline. Well, that jumping up and down can approximate basically what happened with these black holes, where they slammed into each other and suddenly the mass changed dramatically in this one point in space. The person jumping up and down the trampoline is going to create waves that kind of radiate outwards in the trampoline. Like they'll cause the fabric to stretch, and then they'll go back up in the air, and then the fabric will loosen up again and tighten up again, and the sort of this stretching and pulling and contracting and expanding will travel outward in waves around the trampoline. These are the gravitational waves that he was talking about. So that's what he predicted. Now, light from the sun takes about 8 minutes to reach Earth. Where am I going with this? If the sun were to disappear suddenly, like just disappear, there was the mouth pop I was looking for, we would have about 8 minutes before the sun's light would disappear. That's the lag time in communication between us and the sun, really. If the sun disappears, it takes about 8 minutes for us to figure out. So you got 8 minutes to prepare for the end of the world. Although you're not going to know, because information doesn't travel faster than the speed of light, so there's no way anyone would know. It just disappeared, and then we wasted those 8 minutes, playing Candy Crush or whatever. Anyway, that was kind of nihilistic of me. I apologize. We'd have about 8 minutes before the sun's light would disappear. Now, Einstein also proposed that gravity waves, since they travel at the speed of light, we would have about 8 minutes before Earth actually feels the loss of gravity from the sun. Because the sun doesn't exist there anymore, what is there to orbit around? Nothing. But Earth's orbit and the gravity affecting Earth wouldn't actually change until 8 minutes later, when gravity actually caught up to the Earth. And then it goes, whoops, nowhere to go now, and then it just goes flying off somewhere into space. Just somewhere out there. Gravity waves. So, gravitational waves, I should say. I'm sorry, I keep saying gravity waves. It's actually gravitational waves. Gravitational waves were indirectly proven in 1974 when scientists observed the orbit speed of a binary neutron star system was increasing. So basically, as these gravitational waves went up, they would hit the other star, and it would affect the speed of the other star, and then it would send gravitational waves back, and then they would sort of get into this feedback loop, and the waves hit each other. Anyway, it was an indirect proof of gravitational waves. But it didn't actually provide direct evidence of these waves. We never actually saw them. We just saw the result of them. Again, like we've never actually seen a black hole. We've just seen the result of a black hole, which is the black stuff where there used to be stuff. So here's the thing. Gravity does all kinds of weird stuff to us, physics-wise, to physics. One of those effects is time dilation. This is kind of a non sequitur, but we'll tie all this stuff back in. Anyway, time dilation, as I'm sure you guys are aware, is a difference in how time is perceived. How fast or how slow time seems to go for you. Now, that's different from just like being really bored or whatever and having it feel like it takes forever, because time can actually, in a sense, move differently from uh, between two different observers. So clocks far away from a gravitational source will experience time passing more quickly than clocks close to the same source. Which is weird. You would think it was all just relative, in the sense that it's all about how we perceive time, but we've actually shown that how time actually elapses for different for objects closer or further away from a gravitational source can be changed too. So an atomic clock in Boulder, which is far away from the surface of the Earth, and I say surface of the Earth, I mean like sea level. It's actually on the surface of the Earth. It's just in a mountain. Those will actually be slightly faster than an atomic clock at Greenwich, England, which is very much closer to sea level. These have been things that have actually been measured, which is nuts. The idea that time passes differently for two different observers based on how close they are to basically a gravity source, gravitational source. That's one of those weird things in physics that just kind of messes with your mind. Also, it sort of created this thought experiment where you might have two planets, right? You have near and you have far, because we're really good at naming things. And near is near a black hole, and far is far away from it. So you have your dude, your best friend, your girl, whatever. I'm sorry, on planet far. And this planet is far away from a black hole. Now, let's say you and your best friend were born on the exact same day, the exact same hour. So you guys are the exact same age. And you go, hey, I want to go to near. And they go, that's not a good idea because time does weird things by near. You're like, nah, whatever. It's fine. I'll be okay. You'll be okay. Everybody will be okay. Everything's fine. And so you go to near. Well, you go to near, and you have a nice time. You go fly by it and look at stuff, and kind of like, oh, that's nice. Black holes are crazy. And you hang out for a minute, and then you go back to far. Well, from your perspective, time moved exactly the same. You didn't feel any slowdown or speed up. Nothing felt weird. The stuff didn't go ding. Like, nothing was strange. Same thing happened for your friend on planet far. They didn't feel time slow down or speed up. Now, the thing that gets wonky is time passes normally for you. Time passes normally for them. You get back. You're like, yeah, that was a nice trip. It took about 2 weeks. And they're like, oh, for me, it took 5 years. Because you get so much closer to a huge gravitational source that time goes more slowly for you. But you don't feel it. The thing is, if they were to observe you, as you get closer to the black hole, you would start to move more and more slowly. If you got close enough to the black hole, to them it might look like, let's assume you were in some indestructible spaceship and you try to get as close as possible to the black hole. At some point, to them, it would look like you never actually got to the black hole. It would look like you slowed down so much to a point where you just look like you've stopped. Like you're like 5 feet from the black hole and you've just stopped entirely, like so close never to reach it. But for you, time is passing normally. You're just kind of like doo-doo-doo, like going straight down into a black hole for some unknown reason. Maybe you're Matthew McConaughey in Interstellar. Who knows? Anyway, the point being, for both of you, it feels and looks like time is passing normal. But time is actually passing, or time is flowing differently relative to the observer's position. So to you, time looks like it speeds up for them on far. To them on far, time looks like it slows down for you on near. It's all relative. However, for both of you, it seems like your time is passing normally. So black holes, how exactly do black holes get created? Well, black holes are just crazy high mass, super dense, sort of collections of matter out there in the galaxy. And a lot of people say like, oh, a black hole is like a vacuum cleaner. It's actually not technically correct. Imagine that you know, again, to go back to the trampoline thing, imagine that you invented this thing that's like the size of a tennis ball. Like you took a mountain and you crushed it into a tennis ball. So you have the weight of the entire mountain crushed into the tennis ball, and you place that tennis ball on the trampoline. Now let's assume that the trampoline is something that will stretch forever and will never get broken. You place it on the trampoline, you might get something that looks like that. And there's the tennis ball. Because it's just pulling the trampoline way down. So if it were, say, 7 o'clock on top of a mountain, it would be, say, 7:05 on the ground, but how would that work if both heights are in the same general area? I should mention that the reason why we've noticed this with atomic clocks is the difference in the two can be measured in like milliseconds at most. It's such a minute difference when you're talking about distances of that scale from a gravitational source that we've really only been able to measure it with an atomic clock. And how would that work if both heights are in the same general area? See, that's the weird thing about it. If there was a great enough height differential, let's say you lived up here, and this was like Topsburg, let's put it in T, and then there was just like this sheer like Looney Tunes type cliff that went down for like millions and millions of miles closer to the planet, and then there was like I don't know, Cliffsville, let's say C. If the difference was drastic enough, like if this was close enough to the gravitational source, and this was far enough from the gravitational source that you could have like a 5-minute difference, then yeah, they would be that close to each other, and their time would be passing more slowly for these guys than it would be for these guys. Even though, if you were to look at it top down, they might be like that far away from each other. Relativity is weird. It's really weird. It's kind of awesome at the same time that our universe is so strange. So to answer your question, I mean, if they're in the same general area, yeah, time just passes differently for both of them. Again, it's not really enough that you could notice it, but it is. So yeah, your tennis ball, right? Notice that like this has a practically vertical incline near the end, and then there's a larger area where it's just kind of like, it might actually be better to illustrate it like this. Whoops. And there's the tennis ball. So there's a larger area over where the trampoline is affected by the ball. And then close enough to the ball, it's essentially a straight down drop. Now that's the idea with black holes. Black holes are so high mass, and they warp space-time so bad that light is not even high energy enough to basically escape it. Like, light can't even go like, oh, see you guys later. Like, it gets stuck down there. It gets stuck and it never comes back. The most high energy thing that we know of in the universe. Well, yeah. Which is also to say that information doesn't actually ever escape a black hole. So you would never actually see your friend, if you were sitting on far and they were going towards the black hole, you would never actually see your friend hit the black hole, because at some point the light bouncing off of their spaceship, because that's how we see things, we see light bouncing off of stuff and into our eyeballs. The light bouncing off of their spaceship will not actually make it back to your eyeballs, it'll get stuck in the black hole. What if the TV show was aired at a specific time and you had those drastic height differences? Would the airing of the show be affected? Okay, so yeah, let's go back to this. Let's say you had a teleporter, like a Star Trek style teleporter that took you directly from Topsburg to Canyonville or Cliffsville, that's what I called it, and like back up here. And let's say, there was the show was like meant to air at 7 p.m. for both places. Well, you could watch it up here, and then you could teleport down to Cliffsville, and if the time difference was drastic enough, they'd still be watching the show. Like, you could be like, oh no, I missed the last 5 minutes, and it's, 7:45 now, and then you teleport down to Cliffsville, and it's still, 7:20, and they're watching the last 10 minutes of the show. I mean, if we were to go that route, when you're talking about like broadcasting and stuff like that, see, part of the reason why we can do stuff like broadcast at specific times and communicate and coordinate things at specific times is because those differences aren't drastic enough on the Earth. If you had a situation like this, you would have a whole another can of worms. You would have to have probably separate broadcasting stations that would just broadcast on their local time. Here's my little broadcasting tower. It's wonderful, I know. That would broadcast in their own local times, and they would strictly advertise for local time, because you would not really be able to coordinate with, time in the other area. And then things would get weird because, one of the things we have on Earth are time zones. But time zones are constant, more or less, because they're all about where the sun is in Earth's sky relative to somewhere else. It has nothing to do with how differently time passes. In here, you might have different time zones, but it's going to be like a constantly evolving equation to figure out what time it is in the other place, because time is either moving slower or faster there compared to where you are. So you can't just say like, oh, it's 7:05 here, it's going to be like, 8:22 there. It's going to be like, okay, it's 7:05 here, and it's been, let's see here, 300 years since we implemented the timing system. So based on the rate of decay, it's going to be 3 years from now there. Yeah, I mean, it's the heights on Earth aren't really crazy enough to do, like I said, anything beyond like a few milliseconds at most, like probably nanoseconds, or if we wanted to go even crazier, like picoseconds, like just like little tiny bits of like seconds, like enough that it's just kind of like whatever, every few years we might have to like recalibrate things. Yeah. Yeah, it is pretty cool. It's crazy, but like that's the thing. It still exists on the planet. It's just it doesn't actually affect us in our day-to-day lives really at all, unless we're doing something that requires such, you know, time precision between two different parts of the Earth that we would need to worry about that kind of a thing. Um, but yeah, black holes are created when large stars bigger than our sun, have spent all their fuel for nuclear fusion. And nuclear fusion is when you take atoms and you smash them together and you make bigger atoms. and that creates energy because you throw off like electrons and neutrons and stuff like that, and it releases all kinds of like gamma rays and alpha beta particles, and it's crazy high energetic. Suns actually go through stages where they start fusing different types of materials based on, what they can. Like suns like our star, hydrogen, they fuse hydrogen. And then eventually at some point they run out of hydrogen, so they start fusing helium, and then they run out of helium, and they start fusing uh, lithium, and then, beryllium. Is it beryllium? I believe it's beryllium. Boron, and then oxygen. Like eventually they move their way up. Sometimes stars get to the point where they hit fusion, or they hit iron, and they go, well, I can't fuse this, and so they stop. And that's, a few things can happen to a star. Either a star just sort of collapses in on itself. Because here's the deal, stars have a huge gravitational pull in themselves. That's why they don't fly apart. However, the reason why they're so big is because the fusion is releasing so much energy that everything's sort of being blown outwards. It's like this weird stasis where like you've got like a hairdryer blowing into a balloon, but the room that the balloon is in is so high pressure that it's pressing the balloon inwards while you're putting air into the balloon. And maybe there's like a hole or two on the balloon so the air can escape, so that it doesn't like explode or something like that. But you're putting air into the balloon, and then the outside air is pressing the balloon in. So it sort of achieves this state where the balloon isn't really inflating or deflating. It has air inside of it, has air outside of it, and it just sort of stays in the state. Now, fusing different elements can change that. So like stars can swell up as they start to fuse helium together because it releases a different amount of energy. It's still the same reaction, but it has a different result. So it's like you're forcing more into the balloon, so the balloon gets larger. Now imagine the balloon's getting larger and larger and larger and larger and larger, and then your hairdryer or whatever's putting air into the balloon suddenly just like breaks, the motor burns out. That balloon's just going to and then just crumple in on itself, right? If a star is large enough when this happens, it can become a black hole. Sometimes, when this happens, the star slams into itself so violently that the top layer basically gets blown off. Like maybe the top, I don't know how many layers, just a certain amount of material from the star just gets blown off from the shock. In an explosion, and then you get a supernova. Sometimes it slams into itself and everything's okay, and then it becomes like a neutron star where it just kind of sits there and chills, and it's like super dense, but it doesn't really do much of anything except maybe spin really fast. Those things exist too, where you get neutron stars that are spinning like millions of times every second, and they're the size of like Manhattan. It's crazy. But sometimes there's so much mass there that as it's actually collapsing in on itself, it speeds up more and more and more. And it speeds up enough that all of that mass basically goes into a single point, or as close to a single point as you can get it. It becomes a singularity, a black hole. Oh, there you go. Some neutron stars rotate very quickly, some are stable enough to stay neutron stars, and some are dense enough to further collapse into black holes. Very dense, usually around the mass of a sun, but with a diameter of 14 miles. So when I said, like, the size of Manhattan, I wasn't kidding. Imagine taking the sun, making it the size of Manhattan. It's nuts. Let's see here, it's 7:55, so it's... Oh yeah, so how do they detect this? There's a laser interferometer gravitational wave observatory, which is a mouthful, so we call it LIGO because it kind of sounds like Liger, and you know, if anybody's seen Napoleon Dynamite, Ligers are awesome and they can do magic. Basically what they do is they take laser beams, lasers, and they ram them into each other after bouncing them off of mirrors a bunch. Just like bounce them around, align them, and then just like slam the lasers into each other. Not like the things that make the lasers, but the actual lasers themselves. The idea behind this is these lasers are actually destructive. So the idea, the wavelength of each of these lasers is such that when they slam into each other, they actually cancel each other out. So there should be no light left over at the end. If gravity messes with the light beams at all, they're no longer aligned perfectly, and thus not all of the laser is canceled. It's weird, but we know that gravity can affect light because light can't escape from black holes. Gravity can also affect light on a smaller scale. Light can just bend around gravitational sources. So, if there is gravity affecting any of, like, if there is, like, if gravity exerts any influence over these light beams, it's going to bend them ever so slightly. And that means that these perfectly aligned light beams are no longer going to cancel each other out perfectly. There's going to be a little bit that kind of escapes off to the side. You're going to have a little bit of laser light, and you're going to realize that there was some sort of gravitational lensing going on. And these things are insanely, insanely sensitive. They can detect deflections of light within the order of half an atom, which, if we wanted to get into other things which are really hard to think about, it's like detecting the change of half the width of a human hair over the distance between Earth and Alpha Centauri, our nearest star. Well, not our nearest star, but it's almost our nearest star. It's light years away. It's like being able to go like, oh yeah, like that changed a little bit, like this rock just kind of like wiggled on another planet on another star. That kind of sensitivity. So basically the way we were able to detect it is because these gravitational waves from the two black holes slamming to each other finally reached Earth, and they bent the lasers a little bit. And the lasers didn't cancel each other out perfectly. And we went, oh hey, that happened. And it actually happened in a few different places across the country. And we just happened to be lucky enough to set it up in time so that we could see it. It was actually discovered 5 months ago, but, you know, because of peer review, because science, they actually had to review it multiple times and make sure that nobody screwed up at any point in the process, and it wasn't anything else. So before we could finally announce it to the rest of the world, I say we, like I was a part of that discovery at all, before they could announce it to the rest of the world. Yeah, there you go. That's the basic idea. It's the mirrors reflect the lasers, and then if they get any result, then it goes out here and then it gets recorded. So anyway, the punchline of this whole thing, and then I'll let you guys go. Why does this matter? Well, a lot of firsts happened in this test. It was the largest black holes we've ever seen. It was the first time black holes collided that we've observed. It was the first binary black hole. It was the first time we've seen gravitational waves. The first time we've seen anything that isn't in the electromagnetic spectrum. Blah, 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 blah. A whole bunch of stuff. But the biggest implication is how observation of the universe changes. We can have not only electromagnetic observations, but we can now observe the dark universe. You talk about dark matter and dark energy and that kind of stuff. That's stuff that we can't directly observe in the electromagnetic spectrum. And that's the kind of stuff where we go like, where's the extra mass in the universe coming from? Like, why is everything not flying apart or sticking together more? There are these forces that we can't account for in the universe that we don't really aren't able to see. The fact that we've actually seen something for the first time now, not in the electromagnetic spectrum, means that we can now spend time trying to measure if we can, if it's repeatable and refinable, we can spend time measuring gravitational effects on other parts of the universe and sort of fill in those missing parts of the equation and figure out where this extra, gravity is coming from in the universe, why things appear to be more massive than they are at great distances and large sizes, things like that. If this gets better, we might be able to measure the gravitational waves of the Big Bang, when the universe was created. Measuring gravitational waves can help us create a more accurate map of our position in the universe, because we can get an idea of how much stuff is over here and how much stuff is over there and how much stuff is behind us and all that kind of stuff, so we can get a better idea of where we are and further refine that idea of where we sit in the universe relative to everything else. Really, and plus it proves Einstein right yet again. That's one of the crazy things about Einstein is he predicted a lot of stuff that in the 100 years hence, technology improved to be able to discover and see. And it's just insane that one person can come up with so many, at the time, earth-changing ideas in the scientific field that were so widely reviled at the time. When it first came out, they were all like, "This is so dumb," and they came to accept it. And then eventually Einstein became a sort of scientific celebrity. So, I mean, he had vindication before his death. I mean, it wasn't like he spent his entire time and nobody believed him. But, like, the fact that you come up with such radically different ideas about the universe and to have them be proven right over 100 years later. Like, we just now have the technology, and we were lucky enough to see these things over 100 years later. It really says something about the guy and how smart he was. Anyway, I've kept you guys over time, so I'm going to skip the poll questions. If you guys have any questions about anything, feel free to ask me. Otherwise, have a fantastic weekend, and we will see you on Monday. No problem. Have a good one, John. No problem, Caleb. See you later.